Welcome back. In the last video we have seen certain properties of Laplace transform such as shifting properties, scaling properties, a Laplace transform of a periodic function, how to calculate very easily if it is a periodic function which is defined between 0 to infinity, and we have actually seen what is the property of a Laplace transform, that the integral Laplace transform integral is uniformly convergent. So that means you can take the derivative. When you differentiate the Laplace integral, you can take the derivative inside the integral. When you integrate the Laplace integral, you can take the integration inside the Laplace integral of the Laplace transform. So that is what we have seen so far. So let's do some properties of derivatives of the Laplace transform. So let me do this property property number 6. So what we had, if f bar of s is a Laplace transform of f of t, which is a function of s, then, and suppose f is a differentiable function, and what is the Laplace transform of f dash of t and f double dash of t and so on. So what is this one? And Laplace transform of f double dash of t, that means two derivatives of Laplace transform as a function of s. What is it? So these are the questions we have. In general, what is the Laplace transform of n derivatives of function of t, which is a function of s at the end? So what is this one? So let me write this. So what we will have is s times f bar of s, which is a Laplace transform, minus f at 0, the value of function at 0, and here you have s square f bar of s, and then minus s f at 0, and then minus f dash at 0. And what you can easily similarly can guess, it is s power n times Laplace transform of f minus s power n minus 1 times f at 0 minus s power n minus 2 times f dash at 0, and so on. You end up finally s constant times minus this 1 s power 0, and you have s power 0. So n minus 2 plus 1, this is going to be n minus 1. So here s power 0, and you have n minus 1 derivative at 0. That is what you will have. Okay. So if I write functions in the superscript, if I write in the brackets, that is the meaning of derivative. If I don't use dashes, that is the meaning. S power 0 is 1, so you need not write. So this is your formula for Laplace transform of n derivatives. So you can easily see this one just by integration by parts. So what is the Laplace transform of f dash of t as a function of s is, by definition, f of f dash of t e power minus st dt. Do the integration by parts, f of t times e power minus st from 0 to infinity minus integral 0 to infinity f of t times, you differentiate this, you get, so that you get plus s e power minus st dt. So minus minus plus, and you differentiate this with respect to t, that is s comes out, minus s comes out, that minus makes it this place. So this is exactly equal to f at infinity. F is a continuous function which is exponential function, but because s is bigger than order of the exponential function, exponential order, so s is bigger than order of the exponential of this function f. So at infinity this quantity is going to 0. So what you have is minus f naught, f at 0, and this is going to be plus s times, this is f bar of s. So if you rewrite from this side, so you have s f bar of s minus f at 0. So that is first one, and you can do the similar way, you can calculate the same way. So you can calculate the other thing also. So if you do, what is the Laplace transform of f double dash of t, which is a function of s, what you have is 0 to infinity f double dash of t e power minus st dt. Do twice if you do the derivative, integration by parts here. So, you get f dash of t e power minus s t from 0 to infinity, you have minus plus s times 0 to infinity f dash of t e power minus s t dt. So, this is clearly you can see that this is going to be 0 again, because this exponential order is s is bigger than this derivative function. Okay. So, the 0 and you have at 0 minus you have a negative sign minus f dash of 0, this function is 1, and here plus s times you repeat the same thing, you end up getting what we had yesterday, what we had earlier. So, this is this one. So, you can substitute this. So, you see, right, if you write that f bar of s minus f at 0. So, this is nothing but if you put it together. So, you see that s square f bar of s minus f dash of 0 minus f at 0, rather sorry s times f at 0 minus f dash of 0. So, this is second one, repeat n times, you can easily see this what are. So, how to show this one, what you have to show, assume that this is true for n equal to k, you do one more integration. So, you can by one integration by parts will give you at k plus 1 this is true. So, by induction one can show the other result. Okay. By induction we can show the generalized, you can show that Laplace transform of n derivatives of functions of t as a function of s will be s power n times Laplace transform of f minus f at 0, s power n minus 1 times f at 0 minus s power n minus 2 times f dash at 0, and so on. Finally, s power 0 then to f n minus 1 derivative at 0. So, this is what you can easily see. Okay. So, this is one property. Using this one can show. We will look at the other properties. For example, convolution of two functions. How do you find what is its Laplace transform? So, this is property number 7, that is convolution property. If f bar of s is the Laplace transform of f of t as a function of s, and suppose g bar of s is the Laplace transform of some function g of t which is as a function of s, then what we have is a Laplace transform of f convolution with g as a function of t. Then once you take the Laplace transform, this will be a function of s. What is the meaning of this? Let me write what is the definition of convolution. F convolving with g as a function of t. You have two functions. What we do is we integrate from 0 to t f of tau g of t minus tau d tau. So, if you take like this, this is the definition of convolution. So, we do not do it from 0 to infinity, because you have to end up. So, you always if you do like this t minus tau, t is fixed, t is bigger, tau is always less than t. So, you have a t minus tau is always positive and tau is anyway positive. So, that sense, because of this integral makes sense. If you do it from 0 to infinity, if t minus tau, you cannot guarantee that is always positive. Okay. So, that is the reason. So, we do it from 0 to t, you take from 0 to t as a definition of a convolution. So, if you do that, what is the convolution? So, Laplace transform of that convolution 0 to t f of tau g of t minus tau d tau, this as a function of s will be simply product of Laplace transforms, that is f bar of s times g bar of s. This you can easily show. So, what is the proof of this? Proof is not difficult. So, you just start with, you take this inverse transform. So, if you take the Laplace inversion both sides, assume that f and g are such class of functions, class of continuous functions for which you have a which are exponential order, then you have a Laplace transform that exists and it is unique. So, you have inversion. So, its inversion exists. So, such class of function, take the inverse. If you take the inverse both sides, how do I do this integral? So, let me do the proof is let me take this Laplace left hand side, which is Laplace transform of convolution of this, so function of s. So, if I do this integral 0 to infinity f of t, in the place of f of t I have to write this function, that is 0 to t f of tau g of t minus tau d tau times e power minus st dt. So, this is the definition of Laplace transform. So, what we do is, if we have to see how we integrate this, what is this integration, double integration? If you view in a plane, if this is your t axis and this is your tau axis, let us say. So, if this is the line that that is t equal to tau, what happens? T is actually 0 to infinity. So, you take 0 to infinity here t. When you fix t, let us say fix t, and what is tau? Tau is going from 0 to t. So, you are going like this. So, you are integrating like this. You fix your t, you are doing like this. You fix your t, you are trying to integrate like this. So, you fix t, first you integrate tau variable from 0 to t, like that it is going. So, instead of doing this, what I do is I try to fix my, what is t, t is tau. This is how you look at this way. If you look at this way, that means tau is from 0 to infinity. This is same, right? So, this is d tau. So, if you integrate like this, each piece like this, and finally you are adding up, then what you are integrating is basically d tau, that is tau is from okay, you are fixing tau, that is from 0 to tau, 0 to infinity. Where you are fixing? Any one of these places, every place tau is fixed. So, here I fix the tau. If you are doing here, if you start with here, I fix the tau here. So, it is anyway, in any case tau is 0 to infinity. So, 0 to infinity d tau, and if I do this, once I fix this, which is between 0 to infinity, what I am doing is t is from tau to infinity. So, tau to infinity, and inside the integrand as it is g of t minus tau e power minus st dt. Okay. So, this is nothing to do with tau, you can write outside this integral 0 to infinity f of tau, you can put it outside, and because this is tau to infinity, g of t minus tau e power minus st dt into d tau. So, this integral you can evaluate by putting t minus tau as some x variable, new variable, so that you have dt which is equal to dx, because tau is fixed. So, tau is constant. So, you have 0 to infinity f of tau. So, this integral, inner integral, if you can write like when you put t equal to tau, x is 0. When you put t equal to infinity, x equal to infinity for fixed tau. So, you have g of x times e power minus s, t is x plus tau, and then you have dt is dx, and you have d tau. So, this is nothing but 0 to infinity f of tau e power minus s tau d tau. They are separated now. So, integrand is a function of tau and function of x. So, you can write them or you can separate them outside. So, you have gx e power minus sx dx. x is the dummy variable, you can put it as t, x as t. So, what you see is they are nothing but the Laplace transform of f times this integral is Laplace transform of g. So, what we have is Laplace transform of its convolution. This is nothing but f convolving with g as a function of t, as a final form is a function of s is this. So, this is your property which you can use later on. So, using this property we can do some example, we can evaluate some nice relation between beta function and gamma function. Let me use that. So, use the convolution to we can do many things, many convolutions you can make use of this convolution thing to do many problems. So, first one example that I want to do here is a relation between beta function and gamma function. So, you have seen what is gamma function. Let me define what is a beta function. Beta function, if I write beta of mn, let us say, if by definition this is an integral like this, this is a special function which is an integral between 0 to 1 x power m minus 1 times 1 minus x power n minus 1 dx. Such a definition with m positive, n positive, it is well defined function. So, if this is your beta function, you have a relation between, show that what we show is this beta function you can write in terms of if when the mn are integers, or positive numbers, positive reals. So, you have beta mn is actually nothing but gamma m gamma n divided by gamma of m plus n. So, this is what we can show just by using this convolution. So, what I do is I consider I use convolution to show this one. So, let me use f of t as x power m minus 1, let us use, and g of t is x power g of t is t power m minus 1, this is t power n minus 1. So, if I use this, what is f bar of s? F bar of s is, we have already seen if it is a t power alpha, is going to be gamma alpha plus 1 divided by s power alpha plus 1. So, if this is alpha, in the place of alpha you have m minus 1. So, you have gamma m divided by s power m. Similarly, g bar of s is gamma n divided by s power n. So, we can use the convolution, that is f convolving with g, for which you take the Laplace transform. This is f bar of s times g bar of s. Since this is the case, what we have is right hand side is gamma m gamma n by s power m plus n is a Laplace transform of f convolving with g of t, which is function of s. So, you take the inversion both sides, inverse transform of this, so that you have an inverse transform of this, that makes it right hand side f convolving with g as a function of t. So, we need to know what is this one. This is a gamma m gamma n, which is a constant, so you can take it out, gamma n gamma m gamma n. So, Laplace inversion of 1 by s power m plus 1, which is equal to f convolving with g of t. So, we are using the same result, that Laplace transform of t power so this is m plus n, t power m plus n minus 1 is equal to gamma of m plus n divided by s power m plus n. So, this implies gamma Laplace inversion of 1 by s power m plus 1 is t power m plus n minus 1 divided by gamma m plus n. So, just take the inverse on both sides. So, this gets cancelled. So, you have this one, and this is just a constant. So, that comes out and you can divide it. So, this is what you is the result. So, if you use it here, so what you get is left hand side integral 0 to 1 t power m minus 1, that is your f of t, and g of this. So, this is tau. Okay. So, we are using convolution, and g of tau. So, this is t minus tau times n minus 1 d tau, that is the right hand side, which is equal to gamma m gamma n. This is gamma n plus m plus n times t power m plus n minus 1. So, this is the relation that works for every t. Where is this t validity? Validity of t is between 0 to infinity. So, you can take it as 0 to infinity. So, what we require is if I put t equal to 1, if t equal to 1, what we get is a left hand side is the beta function, beta of m comma n, and the right hand side is simply gamma n divided by gamma m plus n. This is what is true. So, we can make use of this convolution to get this relation. What we do is now and you can also see many of the properties of this convolution. Convolution we have defined. What is convolution? Many of these properties that f convolving with g of t is same as g convolving f of t, and many of these trivial properties we can show. It satisfies certain associativity, commutativity, distributive properties. Those are group properties kind of things, so that algebraic properties that we need not worry. So, what is important may be this one at least. You can write this or this, both are same, that you can easily see. Okay. Just by changing the variable, you can easily see that this is true. Okay. So, you have this property, then we move on to get some more properties of this Laplace transform, that is this property number 8. We will see property number 8, that is, you have seen earlier Laplace transform of the derivatives. Now, we can see that a derivative of the Laplace transform, if f bar of s is Laplace transform of f of t as a function of s, then what is the Laplace transform of t power n times f of t as a function of s? This is actually minus 1 power n nth derivative of s derivative nth derivative of with respect to s if you differentiate the Laplace transform. I think of Laplace transform exists for s greater than a, real part of s greater than a. So, you have a domain, s is here. So, s is bigger than some a, s is bigger than some a, let us say a is here. So, everywhere you have a domain here. So, you think of this on this real line, s is between a to infinity, you have real values. In this domain you can differentiate as a real variable. If you differentiate, this is what you will get. So, this is a Laplace transform. What you gain is this is a Laplace transform of some t power n times f of t. So, this is the important property we use to solve differential equations, certain type of differential equations with variable coefficients, special variable coefficients, like you have n derivatives, y n derivatives of x and multiplied with x power n and such integral. So, nth derivative. So, for example, if I write d n y by d x power n, this whole thing you can you take the Laplace transform, you can write n derivatives of Laplace transform of y with of course some negative sign depending on what is your n. even or odd. So, this is the property we use to convert the ordinary differential equation into algebraic equations. When you try to solve variable coefficient equations, we use this property. So, let me show this one. What is the proof of this? This is also straightforward. You can easily prove this. N is this is valid from 0, 1, 2, 3 onwards. Anything you take, this is true. So, if n is 0, this anyway both sides are same. That is actually this. If n equal to 1, you can do this. Do it for n equal to 1. N equal to 1, we show f of t times f of t as a function of s by definition 0 to infinity t f of t e power minus st dt. Okay. What is this one? So, this is if you differentiate so what is this one? So, this is I can write this as 0 to infinity minus sine f of t, and t into e power minus st I write it as s derivative of e power minus st. If what is again minus t e power minus st. So, that minus plus, so this is exactly same as this dt. So, because this is integral, this integral f of t, this f of t into e power minus st is uniformly convergent integral. This integral, this derivative with respect to s, I can take it inside. So, outside and inside both are same. So, I can write dds of f of t times e power minus st dt. So, this is nothing but f minus derivative of dds of f bar of s. That is your Laplace transform of Tf of t as a function of s. So, this is exactly your first one. You repeat the same thing. So, n equal to k, if it is true, suppose n equal to k, assume that it is true, this result is true, then assume that the result is true. Then we can show that n equal to k plus 1, this result will be true. So, how do I do this Laplace transform? So, n equal to k, if I take t power k plus 1 times f of t as a function of s will be minus 1 power k plus 1, rather let me use by definition 0 to infinity t power k plus 1 f of t e power minus st dt. This is the definition of the Laplace transform of this, and this you can write like again you do the same technique, that 0 to infinity t power k times minus t I am writing as a derivative of dds of e power minus st dt. This is same as this. So, you can take this derivative outside, that is minus of dds of this is Laplace transform of t power k f of t. What is left is there. So, you assume that this is result is true. So, minus dds of Laplace transform of this, right. So, in the place of this you can put it minus 1 power k times d power k by ds power k of f bar of s. Of course, this is a function of s, that is why you are able to do this. Okay, this is equal to, so minus 1 power k plus 1 derivatives, I have now k plus 1 derivatives of f bar of s. So, this is exactly what is true. So, if n is true, n equal to k, it is true, n equal to k plus 1, the result is true. Hence, by induction the result is true. Okay. So, this is another property we use later on when we solve the differential equations. And then property 9, I can do some examples. will do some examples just to give you a feeling. So, an example is Laplace transform of t power n times e power minus at. What is this one? This is equal to, so you want to find t power n when you multiply, what happens? T power n e power at. So, this is, if you use that formula, this is going to be minus 1 power n derivatives of s, which is of function, so Laplace transform of e power minus at, which is function of s. So, this is minus 1 power n derivatives of with respect to s. What is this Laplace transform of this? Is 1 by s minus a. So, you differentiate this, you end up getting you n times differentiate, every time you get a negative sign. So, you have minus 1 power n times 1 by s minus a power n plus 1, and you have n factorial comes up in the numerator. So, this is going to be 1. So, you have n factorial divided by s minus a power n plus 1. So, this is one example where you can use. So, if you have a t power n multiplication with a known function whose transform if you know, you can easily work out a product of these functions. So, let me do some more examples. One more example, you can think of Laplace transform of t times cos at. So, if you have a function like this as a function of s, this is minus, because this is a t multiplication with t. So, you have minus times 1 derivative of f bar of, so Laplace transform of cos of at, cos at, which is function of s. So, this is equal to minus t ds of, what is the Laplace transform of cos at? That we know that it is actually s divided by s square plus a square. If it is a sin at, if you have a sin at, if instead of cos you have a sin at, what we have is, we will write either this or cos at or sin at, let us say it. Okay. So, sin at or cos at or sin at, both the things you can look at it. So, either this or a divided by s square plus a square. So, this is what you have to do, either this or this depending on cos at or sin at. So, what you end up is a minus s square plus a square whole square. So, you have s square plus a square minus s times 2s square. So, you have a minus s square comes out. So, a square minus s square. So, with minus sign you have s square minus a square divided by s square plus a square whole square, either this or, and you have a minus derivative is s square plus a square whole square, s square plus a square times a, that is 0. So, you have a minus minus plus, and you have a times 2s. So, 2as divided by s square plus a square whole square. So, either this or this depending on your Laplace transform of t times cosine of at or sine of at. So, you will see this result too. So, we have used derivatives so far. We can also get some more property of one more property of Laplace transform, that is in terms of the integral of the Laplace transforms we can work out. So, let me take this as a property 9. So, property 9 is, so we will write what the property is. If I have a Laplace transform which is a function of Laplace transform of t, f bar of s is Laplace transform of f of t, then a Laplace transform of f of t by t. Now, you have this one, if you have a division with t instead of multiplying, what you get is actually integration from s to infinity f bar of s ds as a real variable. S is a real variable which you are integrating from s to infinity. So, this is where we use a property of uniform convergence of the Laplace transform integral. Okay. So, this proof is also simple. So, you start with what you want to have. Let us start with the right hand side. So, if you start with the right hand side, that is from s to infinity, f bar of s, you have 0 to infinity f of t e power minus st dt, this is ds. So, you see this integral is uniformly convergent integral, that f bar of s. So, you are differentiating, you are integrating with respect to s from s to infinity. So, this integral I can take it inside because of uniform convergence. So, 0 to infinity I can do from s to infinity f of t e power minus st dt ds. So, this s integral I can take it inside. So, that is what this integration we are doing inside. So, that you can write this here and e power st. So, f of t you can put it here. So, this integral you can evaluate. If you do that evaluation, so what you get is, if you evaluate that, you see that 1 by s e power 1 by t. So, rather e power st of t, this is from s to infinity, integral 0 to infinity f of t dt. So, what is this integral? This is e power minus st, right. So, there is minus st. So, that is missing. So, we have minus st, we have minus. So, we have minus here. So, at infinity again of course, we are doing s integration. So, s equal to s to infinity. So, when you put s equal to infinity, this e power minus st, because t is always positive. So, t is positive. So, that means this at infinity is going to be 0 and minus minus plus you have e power minus s equal to s only st by t. This is from integral 0 to infinity and f of t dt. So, this is nothing but Laplace transform of f of t by t as a function of s. So, this is exactly your right hand side, left hand side of your property. Okay. So, this is how we show that if you have integration or if you have 1 by t times of function, which you know already what is the Laplace transform of f, then you simply integrate that to get the Laplace transform of 1 by t times f of t. So, we can do similarly, we can do some examples such as what is the Laplace transform of sin a t by t. This is again, so by directly if you use s to infinity, Laplace transform of s sin a t, that is a divided by s square plus a square, we have ds. So, a comes out s to infinity ds by s square plus a square. So, this is equal to so a square you take it out. So, you have 1 by a comes out s to infinity ds ds divided by 1 plus s by a whole square. Okay. So, this is nothing but so you can also take this and you write d of s by a. So, this is nothing but tan inverse s by a right. So, this is equal to you write s by a equal to some t some x. So, you have dx by 1 plus x square integral s by x is that. So, x is when you put x equal to s. So, you have s by a. Okay. So, this is if you actually properly do it, put s by a equal to x. So, you have dx by 1 plus x square. X is now when you put s equal to a s equal to s by a, s equal to s. So, you have s by a to infinity, and you put s equal to infinity, that is actually infinity. So, this is nothing but a tan inverse x from s by a to infinity. So, what is this one? Tan inverse infinity, that is pi by 2 minus tan inverse s by a. So, you can, this is also same as tan inverse a by s by the properties of inverse trigonometric functions. You can see this one. So, like this you can use this property if you know the Fourier transform, Laplace transform of some function. If you want to find the Laplace transform of such function who's multiplied with 1 by t, you can use this property to evaluate the Laplace transform. So, I stop here, and we will see some more properties and actually how to find what are the ways to find the inverse transform. So far we are only doing with dealing with how to find the Laplace transforms, and we will see the properties how to find the inverse Laplace transforms. And finally, before we move on to apply these Laplace transform technique to solve in the applications of solving differential equations and other areas. Okay. So, we will see in the next video. Thank you very much.